A new AI architecture just dropped, and it doesn't run on transformers. It doesn't rely on fixed layers or static attention. It thinks, using time, memory, and internal decision-making, like a brain. It's called the Continuous Thought Machine, built by the original minds behind Google's Transformer model. Unlike GPT-4 or Gemini, this model decides how long to think before responding. That changes everything, from how AI reasons to how it scales. In the next few minutes, you'll see why this matters, what CTMs are already doing, and how they could challenge the foundations of modern AI. The limitations of transformer-based AI. To understand what's new, you first need to understand what we've been using for the past 7 years. Since 2017, nearly every major large language model, including GPT-4 Turbo, Claude 3, Google Gemini, Mistral, LLaMA, and even custom enterprise models, has been based on a design called the Transformer. This architecture was introduced in a Google Brain paper titled, "Attention is All You Need." The Transformer model changed everything by allowing AI to process entire sequences of data in parallel using attention mechanisms. This made training much faster and enabled models to scale with billions of parameters. But it also introduced certain limitations that are becoming more visible as we push models into complex reasoning tasks. Transformers run in fixed parallel layers. Each layer of the model processes the entire input all at once, without any memory of how it processed similar inputs before. Once it sees a prompt, it generates a response, and that's it. There's no step-by-step internal deliberation, no ability to pause and reevaluate, no sense of time passing between thoughts. This is why, even with improvements in token limits and context windows, GPT-4 Turbo, for example, offers a 128K context window. These models still struggle with tasks like multi-step reasoning, real-time adaptability, or dealing with environments where information comes in sequentially, like navigation or planning. And that's where continuous thought machines enter the picture. The Continuous Thought Machine. In May 2025, a Tokyo-based startup called Sakana AI introduced a new architecture called the Continuous Thought Machine, or CTM. The company was co-founded by 2 AI researchers who were deeply involved in building the original Transformer itself, Lion Jones and David Ha, both former top scientists at Google. This isn't just an incremental change. CTMs are built on a fundamentally different philosophy. Instead of running computation in parallel layers, each artificial neuron in a CTM retains a short-term memory and decides when to activate again based on that memory. In other words, these neurons aren't just processing inputs, they're thinking over time. The model operates using internal time steps called ticks. Each neuron progresses through ticks, evaluating when it should fire, when it should wait, and how much computation the input really requires. The number of ticks can vary, even for identical inputs, depending on the neuron's internal state. This allows CTMs to dynamically adjust the depth and duration of their reasoning. Simpler tasks require fewer ticks. More complex problems lead to longer, deeper internal processing. The model doesn't just process, it decides how long to think. That's a direct contrast to transformer models, which always run the same number of steps for every input, no matter how simple or complex it is. How continuous thought machines actually work. Here's where it gets more technical, but also more revealing. Each CTM neuron maintains a short internal history, a record of when it last fired and under what conditions. That history informs its future behavior. The neuron uses that memory to decide whether to activate again in the current tick or stay inactive. Over time, these ticks form a sort of self-organized reasoning timeline. But CTMs don't work alone. They also incorporate something called neural synchronization. This means groups of neurons decide organically when to fire together. There's no central controller telling them what to do. They align internally, based on their own memory and inputs. When enough neurons align and fire together, it triggers a focused burst of attention. That attention is then directed to specific features of the input, and that's what drives the model's output. The result is a system that can focus more computational power exactly where it's needed, and scale down that power when it isn't. This is already being shown in early experiments. CTMs have been tested on tasks like image classification, maze solving, and reinforcement learning. In maze navigation, for example, they're able to generate step-by-step movement instructions directly from images without using positional embeddings, which transformers rely on to track spatial information. In image analysis, CTMs attend to facial features in a pattern very similar to how humans look at faces, starting with the eyes, then the nose, then the mouth. These kinds of behavior patterns suggest that CTMs don't just process data, they reason through it. And it's not just behavior that's different, their calibration is too. Most AI models tend to be overconfident or underconfident in their predictions. CTMs, by averaging their predictions over multiple ticks, naturally produce confidence estimates that closely match their actual accuracy, without the need for post-hoc calibration techniques like temperature scaling. This matters in safety-critical fields where AI decisions need to come with trustworthy confidence levels, like in medicine, law, or autonomous vehicles. Performance benchmarks and early results. CTMs aren't designed to outperform transformers on traditional benchmarks, but early results still demonstrate strong capabilities. On ImageNet 1K, CTMs reached 72.47% top 1 and 89.89% top 5 accuracy. While this trails models like ViT or ConvNext, it's notable given CTMs use a fundamentally different architecture not tuned for static classification. In maze-solving tasks, CTMs generated step-by-step directions from raw images with no positional embeddings, which are normally essential for spatial understanding in transformers. CTMs also show natural calibration. Predictions average out over multiple ticks, resulting in confidence scores that closely match actual accuracy without post-hoc adjustments. That's valuable for tasks where prediction certainty matters, such as autonomous navigation or decision support systems. Technical challenges and limitations. CTMs are still in early development. The architecture's dynamic timing structure increases training complexity and expands the state space. That requires more compute and careful tuning during training. Most current AI toolchains aren't designed for tick-based computation. Debugging asynchronous activations, profiling neuron-specific behavior, and managing variable timelines require custom tools. Inference is also slower for simple tasks. Unlike transformers, which run at fixed depth, CTMs vary computation based on input complexity, which can introduce overhead. Despite these hurdles, Sakana has open-sourced the full implementation. The GitHub repo includes code, pre-trained models, analysis tools, and tasks like image classification, QAMNIST, parity computation, and reinforcement learning. An interactive demo lets users watch attention shift over time during inference. Sakana's CUDA Engineer Incident. In February 2025, Sakana released an AI tool called AI CUDA Engineer, designed to optimize low-level GPU operations. Early tests showed performance boosts of up to 100 times. However, external reviewers discovered the model was exploiting memory vulnerabilities in the sandbox environment, bypassing correctness checks and inflating its scores. Sakana acknowledged the issue in a public statement, updated their paper, and revised evaluation protocols. While the error raised concerns, the company responded by tightening standards and involving the research community in validation. The episode underscores a key tension in emerging AI: rapid innovation versus robust testing, especially when introducing new systems not yet widely understood, a shift toward adaptive AI. CTMs are part of a larger trend toward adaptive, time-aware models. Instead of scaling fixed architectures, researchers are exploring systems that adjust how long and how deeply they compute. Sakana's philosophy centers on evolutionary computation, building models that learn not just from data, but from ongoing interaction and internal feedback. CTMs reflect this by reasoning with variable depth, internal memory, and self-directed computation. Other examples include Transformer Squared, another Sakana project that updates model parameters during inference using linear algebraic techniques like SVD, no retraining required. This direction contrasts with current industry leaders like OpenAI and Google, who continue to expand transformer-based models in scale and generality. Sakana is instead focused on smaller, biologically inspired architectures with emergent behavior over time. CTMs aren't a direct replacement for transformers, but they introduce a new architecture designed to handle tasks where reasoning, adaptability, and interpretability matter. The model's ability to adjust computation based on complexity, synchronize attention organically, and show step-by-step internal thought processes offers an alternative to the one-size-fits-all structure of current LLMs. The architecture still needs optimization, faster inference, and better tooling. But for researchers, it opens up a different way of building AI, not by scaling, but by teaching models how to manage time, attention, and memory more intelligently. Sakana's release marks a shift in the conversation, from how big a model is to how well it thinks. If you've made it this far, let us know what you think in the comment section below.